So hello everyone, welcome back. Today we will continue our discussion on operators in the occupation number basis. So we start from reminding ourselves the wave function in the occupation number basis. So the wave function in the occupation number basis is something like this, which can be constructed out of the product of the. So this is I'm writing down the occupation, the element of the Hilbert space in the occupation number basis. And this we are writing as a product of single product in terms of the product representation. So this is and then there is a sum over all distinct permutation. Okay, and then there is a normalization factor, and the normalization factor is n1 factorial times n2. So this is the inverse of this is the number of distinct permutation. So that's why we are multiplying it to make it ortho normalized. Now we will consider some general operators. Some, let's say, single particle action of a single particle operator. Okay, so let's say there is some operator f which takes a state from I and maps it to j. Okay, in principle there can be summation over I and j, but we are ignoring that aspect for the moment. We are not assuming any summation over I and j. So these are the possibilities, and then if this is the case, then there are, for simplicity, assume that I and j to be some fixed number. Okay, later we can relax this condition because we will see that the final result we can always do the summation over I and j. Okay, so for this moment, that's why we are doing this. Then there are two distinct possibilities, that I is equal to j or I is not equal to j. Okay, so the operator can be diagonal. This means the operator is diagonal. And the other one is not. Okay. So now, if I is equal to j, then all the occupation number remains the same. Under this action, under the action of if. Okay, so that means, which also implies that action, f is diagonal so sorry, I have to make some distinction. So this is a single particle operator. So this discussion is just about this discussion is about the single particle states, and now we are seeing that what happens in the multi-particle state, and this is the, so let me actually denote it by a color. This is the operator in the multi-particle Hilbert space, which is basically sum over single particle Hilbert operators. This is also multi-particle operator. Which is simply sum over the single particle operators. Okay, so the action of f diagonal in the occupation number basis. So we take this thing, the multi-particle operator, and our claim is that this object is same as Ni Fi. There is no summation over I. If there was in the initial stage we fixed I to be some fixed number, and that's why there is no summation over I. If there was not that restriction at the initial stage, then there would have been a summation over I. Okay, so this is the claim. So where Fi is Fi is just the expectation value. Fi is the expectation value in the single particle Hilbert space. So this is the single particle operator again. Not red f. And this is the expectation value in the single particle operator, and Ni is just the number of the states. So this answer sounds very intuitive, because it's basically we have Ni such states, and each such states give you Fi. So that means the total result is just Ni times Fi. Okay, so this is the thing, but a rigorous derivation of that we'll see in the next section, and that part actually goes, that part will be very helpful. The similar proof will go also for this. So we'll only do rigorously for I not equal to j, because that's the more difficult case. So in the I not equal to j case, what happens is that because I not equal to j, the occupation number of ni reduced by 1 and the occupation number nj increases by 1. Okay. So if that's the case, then the non-zero matrix element will be something like n1 ni minus 1 nj plus 1 n1 ni nj, and here we are inserting the operator f. Okay, so let's now try to compute this thing. So firstly, from the normalizations, so you remember there was an important normalization factor here, so we will put that expression there. So we'll put this whole expression there and try to compute it. We'll put this expression and try to compute it. So from this normalization factor we get n1 factorial dot 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 ni minus 1 factorial nj plus 1 factorial by n factorial power half, and then ni factorial n1 factorial n factorial nj factorial by n. This is the thing. So this just comes out of the normalization. Then you remember that there was a sum over all permutations, all distinct permutations, right? So firstly, the important thing we get is that this following quantity. So this is basically the sandwich if I take the FR operator and sandwich between two such states. I mean, there will be one such thing. I mean, it's a product of n wave functions, but one of these wave function contribute here, and the other wave functions are simply multiply with its corresponding gate to give you 1. Now question is that how many such terms are there? How many such terms we get? This will be generated by the permutations, and the permutation is simply n minus 1 factorial, because 1 has been already assigned here, right? So in order to choose that, we already have chosen these states to be very particular. So we are left with n minus 1 particles, so n minus 1 factorial, and from that n1 will go to state 1, ni minus 1 factorial will go to state 2, and nj factorial will go to state j, right? So I'm just looking at this part, because this part will be automatically fixed by orthogonality. Okay, so this is the factor that we will get, that what are the number of states starting from n minus 1 particles, and we have to distribute them to n1 nj and ni minus 1, because 1 already is chosen here. So that's why this is ny minus 1. And then if you put all this thing and simplify this expression, then this expression simply becomes this is my Fij. So this expression simply becomes nj plus 1 ni square root Fij. Now this expression looks very familiar. This expression is analogous to something that we have already observed, that we have seen in harmonic oscillator. Okay, so that is basically the motivation, that you remember that in harmonic oscillator, if I have a dagger, the creation operator, it acts on state n, it gives you some square root of n plus 1 and then n plus 1. And if the annihilation operator acts on state n, it gives you square root of n times n minus 1. Okay. So now, because of this, let's try to have a set of operators we are postulating this set of operators, which is roughly, we are calling it AI, parameterized by I, such that AI is a dagger, the commutator is delta ij, and the creation operators, they commute with each other. Okay, so basically you can think like it is like it's like a set of harmonic oscillators rather than one. Okay, but at this point it is not at all obvious that why we are getting something like harmonic oscillator, but just this formula is very instructive, and that's why we are writing in this way. So if that is the case, then you see that we first denote vacuum to be the state which is all annihilated by all the annihilation operators. So all the annihilation operator annihilates these states. Okay, so that means that if I have some state which is n dot 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 ni dot 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 nj, something like this, then this is basically what this is like we have constructed out of harmonic oscillators is a1 power n over square root n factor n1 factor, sorry, so a1 power n1 over square root n1 factorial, a2 power n2 over square root n2 factorial, and dot 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 acting on this factor. So you notice one thing we already discussed in one previous lecture, that this vacuum state, this state with no occupation, this has no analog in the product basis. There is no analog in the product basis. Okay, so this is only something we can write only in terms of this creation and annihilation operators. But once I have written in this form, then you see that the operator F, the multiparticle operator, sorry, we are writing it in color. This can be just simply written as okay. So this can simply be written in this way. So this representation is called the representation in the occupation number basis. Okay, so this is the important thing you notice here is that it automatically knows about the statistics. I mean, to be more precise, this factor is due to bosonic statistics. This factor really comes out of the permutations, which is really the consequence of statistics. And if all these particles were distinguishable, then we would not have got this factor. So this factor is consequence of statistics. And you see that this form, it automatically knows about the factor due to statistics. In other words, statistics is inbuilt into this form. And hence, the occupation number basis is a more natural language to talk about multiparticle, to discuss multiparticle quantum systems. Okay, so what we have seen is that basically we have taken a single particle operators and we have represented in the occupation number basis.